So, good morning, guys. Today we're going to be jumping in, taking another look at condensation heat transfer, hopefully getting into some discussions on calculations associated with condensation heat transfer and working some examples. So, getting this going for the day. Today we're going to be focusing on condensation heat transfer. And so from last time I stated that when we're looking at condensation, we're looking at a system where the temperature of the vapor is going to fall somewhere around or slightly above the saturation temperature. And we can accomplish this by bringing the vapor into contact with a solid surface whose temperature T sub S falls below the saturation temperature. Also, it's important to know that unlike when we talked about boiling, condensation can occur when discussing about contact with other liquids or vapors. And we have two distinct forms of condensation. What were those forms? Do you guys remember from Friday?
Film condensation and dropwise condensation.
Thank you. We have film condensation and dropwise. And so the major difference is that we have the condensate forming a solid film, or I shouldn't say solid. Of a given thickness. Delta. And the thickness of the film increases in the direction of flow. And also, we find that the film causes or results in the presence of a heat transfer resistance. Which I'll talk about here in a minute. This differs from dropwise, which I'll give it some space. Where we have the vapor condensing into droplets on the surface instead of a continuous film. What's a good example of this?
Dew on like grass.
That's another good example. Condensation on a drink. Right. So if I got like a can or a glass of water, soda or something, you're going to see those droplets form, especially in Mississippi between the months of April through October. And so what we find is that since in dropwise condensation, we don't have, there's no secondary heat transfer resistance. We do find that the heat fluxes associated with dropwise condensation are about 5 to 10 times the heat fluxes we see in a film condensation. However, while dropwise condensation is more efficient, it presents a self-limiting case because dropwise condensation quickly becomes film condensation. For most systems. Which means unless you have a really good way to keep that film from forming, you're always going to have that film kind of essentially develop and limit your heat transfer. So looking at film condensation in detail, because that's where we're really going to focus, is that for film condensation, we find a similar approach to forced convection in that our flow regime is a strong indicator of heat transfer performance. Or I could just say TDLR, flow regime, tells you what equation to use. Here, I'll zoom out to give you guys a second to catch up. All right, which means we need to find our handy dandy Reynolds number. which once again means we have to define what the Reynolds number is for condensate flow. And we can say it's the hydraulic diameter times the density of the liquid times the velocity of the liquid as it's flowing over the viscosity of the liquid. I can also calculate it as 4 times the density of the liquid times the velocity of the liquid times delta, or the thickness of the film over the viscosity of the liquid. And if I'm given mass flow rate, I can say it's 4 times mass flow rate over the density of the liquid times viscosity. Which means the hydraulic diameter is going to be 4 times the thickness of the liquid. And I have no idea why that just disappeared. And these are all subscripts just to tell you that it's of the liquid, not the vapor in the system.
Did you just write that DH is equal to 4 rho or 4 delta? Excuse
Yep.
me.
Yeah, the hydric diameter is just 4 times the thickness. It's also, you can calculate it as 4 times the cross-sectional area of the film over the wetted perimeter of the film. But those values are a function of the geometry in which the film is forming on. What's universal to all geometries is just 4 times the thickness of the film.
Is this only true in circular pipes?
Nope. It's true for all systems.
Okay.
Here, just for completeness. I'll write this down. Condensate film thickness AC is the cross-sectional area of condensate flow and P is the wetted perimeter. You guys still there?
Yeah.
Yeah.
All right. It seems I had an internet hiccup.
I thought it was me for a second. I was very concerned.
Go back. So looking at Reynolds number again, you can say Reynolds number is essentially rho UD over mu when we're looking at liquid properties, and the D is the hydraulic diameter, which is given as 4 times the condensate film thickness. Or if you want to calculate it as basically 4 times A sub C, which is the cross-sectional area of the condensate flow over the wetted perimeter. All right. So with that in mind, we also need one more piece of information to determine our anticipated heat transfer rates. And that is what's known as a modified enthalpy of vaporization. which I'm going to call Lambda Star. And the purpose of Lambda Star is given a system where I've got a surface here, T sub S. I have a liquid film forming with flow, and I've got some vapor. The temperature of the fluid will be slightly below saturation. Due to the fact and the existence of it as a heat transfer resistance, meaning the energy going into condensing this fluid is going to result in essentially more energy needed than what you might expect. And so we have to correct for the fact that that temperature of that liquid film isn't going to be at saturation, but slightly below. And we do that by calculating what's known as a modified enthalpy of vaporization. And so lambda star is equal to traditional lambda plus 0.68 times the heat capacity of the liquid times T sat minus T sub S. And so this signifies kind of condensing the liquid. And this is cooling below. So we can get the net energy. Loss from fluid. But wait, there's more. If you act now, we can also talk about corrections for condensation involving superheated vapors. Where if you're in a system where the vapor isn't coming in at saturation but being superheated, we can calculate a updated modified enthalpy of vaporization as lambda plus 0.68 times the heat capacity of the liquid times Ts minus T sat plus the heat capacity of the vapor times temperature of the vapor minus T sat. Which is, once again, this is the net energy loss. This is the energy to cool fluid to saturation. Then we have condensing the liquid. And cooling below saturation. Which means instead of putting it in our expressions, it's far easier to simply correct our enthalpy of vaporization and put that in our expressions that are a function of Reynolds. And I'll zoom out one more time so you guys can get a quick look.
Hey, Dr. Lopez,
Yes, sir.
is there a reason that TSAT and TS are switched in the liquid cooling below saturation temp in the first equation versus the second form?
No, thank you.
Okay.
It should be Tsat minus TS because TS will be less than. Thank you. The only reason is that apparently I can't talk and write at the same time. And so with this in mind, we can express the heat transfer rate or Q condense as HAS Tsat minus TS or M lambda star. Right? Because if I say this is the net energy loss per unit mass, if I multiply that times my condensation rate, that is my heat transfer rate. Or what I can do is calculate, given a surface area for condensation, my deriving force, that is the temperature saturation minus the surface temperature, we can also calculate a condensation heat transfer coefficient. If we're looking for that condensation rate, which we often are in these systems. So depending on what we're interested in, we can either be looking for condensation rate, heat transfer rate, or heat transfer coefficients. And so we can find our heat transfer coefficients by knowing something about our flow regime as well as the geometry of our system. So I'll say our H is going to be a function of, once again, Reynolds, as well as system geometry. So for our first system, we can consider condensation on a vertical plate. And so what we can say is for laminar flow, which I believe in this case, our Reynolds number should be less than 30, I believe. We can say our heat transfer coefficient for laminar is equal to approximately 0.943 times the quantity gravity times the density of the liquid times the density of the liquid minus the density of the vapor times our modified enthalpy of vaporization times the heat capacity of our liquid divided by the viscosity of our liquid times our Tsat minus Ts times our L, which is the height of the vertical plate, all to the 1/4 power.
Is that KL?
Is that what?
K sub L?
Yes, K sub L. Actually, no, this is just laminar in general. So this is just for laminar in general. We can simplify, that's what it is for low Reynolds numbers, which is less than 30. We have a simpler expression also where rho V is much less than rho L, which is like most systems, unless you have high pressure involved. We can also say H vert is equal to 1.47 K sub L times Reynolds to the negative 1/3 times G divided by V sub L, kinematic viscosity of the liquid, to the 1/3.
Dr. Lopez,
Yes.
what type of ratio is much less for the densities?
Probably 2 orders of magnitude.
Okay. Thank you.
Oh, you're welcome. Like for water, for example, right? The density of water is 1,000. For water vapor is usually 1 or less than 1. And so in that case, I would consider that to apply. That's why I say for systems atmospheric pressure, 9 times out of 10, it's going to apply. It's only when you have high pressure systems that you have to consider it, because then the densities of the vapors are going to be much higher as compared to the liquid.
Is that the velocity of the liquid? Geo for the velocity of the liquid?
It should be the kinematic viscosity. Let me double check. Yeah, it's the kinematic viscosity.
Thank you.
We can actually, let's do a double check. This is points square Kelvin. This is watts per meter Kelvin. So this needs to be what? End up in meters. So in the parentheses, we have meters per second squared, which means I need to end up with a bunch of meters on the bottom. Now this is squared. Double check my notes again. Yeah, it's G per B sub L squared. So I need the meters to cancel. So if it's meters squared per second squared, this gives me what? 1 over meters cubed to the 1/3. So it's kinematic viscosity. Quick unit check lets me confirm that. When in doubt, figure out what the units need to be. What the units need to be tells you what property you need. One of those things that you don't know why it works, but it somehow works. feel like engineering needs to have a big convention where we decide new symbols for all of these properties and then commit to only use one symbol per property.
And then they can also discuss moving fully to SI.
Yeah.
That would make life too easy, though. And then engineers might actually start enjoying their lives.
Yeah, but I would kind of look forward to the bumper stickers on the back of trucks and the flags that says, you know, English units forever.
Just no. I hate English units.
I definitely think it would help with the teaching aspect, but I feel like engineers in the field probably just made up their own values.
Yeah, it's like we don't need those units. You see this? This is a piece of wood. All you need is this piece of wood. And all these marks I've made over 20 years.
Yeah.
It's like the measuring buckets that people make up.
Exactly.
Well, this line's 3 gallons.
So moving on, for Reynolds above 30, we see waves form at the liquid vapor interface. We consider this wavy laminar, meaning we need another equation to describe it. Let's over a wavy laminar flow, which I'll call wavy. We have a Reynolds number times the capacity of our liquid divided by 1.08 times Reynolds number to the, I believe, 1.22 power minus 5.2 times gravity divided by kinematic viscosity of the liquid squared to the 1/3. And this is between Reynolds numbers of 30 and 1800.
Is that Reynolds number for the vapor or liquid phase?
For the liquid.
I love how it's called wavy laminar.
Yes. And if you wanted to calculate Reynolds number in the wavy, you can calculate it using this expression, 4.81 plus 3.70 times the height of the plate times the heat capacity of the liquid times Tsat minus T sub S divided by viscosity of the liquid, enthalpy star, G over kinematic viscosity of liquid squared to the 1/3, all to the 0.820. This is simply just combining this H equation here with our Reynolds number expression beforehand. So I probably wouldn't recommend using it unless you were missing some piece of information so you couldn't use the other Reynolds number expression. And so at Reynolds numbers above 1800, we consider the fluid, or the flow is considered turbulent. So for turbulent flow,
Can you scroll up just a little bit? Sorry, I didn't finish.
you're good. I don't blame you. Here, I can zoom out. It's probably even better. So the heat transfer coefficient for turbulent flow is Reynolds number times thermal conductivity of the liquid divided by 8750 plus 58 times the Prandtl number to the negative 0.5 power times Reynolds number minus 253 times our gravity expression over the kinematic viscosity of the liquid to the 1/3. I always think these equations are interesting because it's like this is what happens when we can't do good analytical solutions and we have to do empirical stuff. All right. You guys caught up?
Yes, sir.
So now I would say is we've been talking about vertical plates. So how would tilting the plate influence our expected heat transfer rate?
I feel like we're about to see some trig. Tilt.
And so plate like this versus plate like this. Condensation. Condensation. Which one's going to have a higher condensation rate?
The vertical one.
Why?
Because the liquid will be able to fall down more quickly on the vertical surface rather than on the tilted surface. And because the liquid will build up on the tilted surface, it'll increase the resistance on the tilted surface, causing a decrease in heat transfer.
Does anyone agree? Disagree? Silence. Does Holly's cat want to weigh in?
I'll disagree with that, Dr. Lopez. I think if you tilt the plate, it'll spend more time in contact with it, and that'll increase the heat transfer.
Okay. I like that. I can respect that. Well, for an incline plate, we do see a slight decrease in heat transfer rate, as well as our heat transfer coefficient. We can calculate the correction using a very simple expression where we calculate assuming it's vertical, then we apply trig correction So yes, trig is involved. Oh no. And that will allow us to identify the expected heat transfer coefficient for a plate that is not a true vertical plate.
I knew it.
Is theta the angle it makes with like the y or the x-axis?
Ooh, that's a good question. It would be the angle it makes with the y-axis. So if I drew it like this, theta would be here. Very good question. Right, because if cosine was if theta was 0, right, cosine should be 1, and 1 to the 1/4 power is 1, which means we're left with the vertical. Any questions on that?
Is there a difference between condensing on that right side of the plate versus condensing on the left side of that plate when you have it inclined?
Like this?
Yeah, like that was your condensate side versus the right side.
That's a really good question. And I would say, yes, it will definitely influence what you expect with your condensation rate. And I would argue that the film that you have form, let's say on this side, is going to be much thinner than what you have on the other.
Yeah.
And so in terms of analysis, I would focus on the side with the greatest heat transfer resistance.
Yeah, just my initial thought was like, if you do it like that, you don't have like the plate resisting the fall of
Exactly.
the droplets. But you still have the same surface area like down into your flow.
Exactly. So you might see heat transfer rates on that other side more similar to what you expect for dropwise condensation. And so in that kind of system, you might have to consider what's the word? Basically doing an analysis on both sides. However, that also assumes that the vapor is in contact in both surfaces.
Mm-hmm.
In a lot of systems, the vapor is typically only going to be in contact with one side.
Yeah, I just didn't know if like your condenser geometry was more like in line with that left side of the plate, like the contact surface with your vapor.
Yeah.
If it would be a better system.
Yeah, that's a good question. But yeah, that gets into more of some of the dropwise analysis. All right, so while all this vertical plate stuff is helpful, what we might consider is that one of the more common things we're going to look at is condensation on a horizontal tube. Because if we're looking at a heat transfer system or we're looking at a heat exchanger, we're more often going to be condensing on the shell of a shell and tube heat exchanger. Which means we have to consider, well, we're changing geometry as well as the orientation. So then what the heck is our expected condensation rate for a horizontal tube? And that expression is 0.729 times gravity times density of the liquid times density of the liquid minus density of the vapor times enthalpy star times thermal conductivity of the liquid divided by viscosity of the liquid times our Tsat minus Ts times our diameter of the tube, all to the 1/4. I think we're about out of time. And I will say, while the vertical plate stuff is interesting and helpful, this is probably going to be the most applicable one that we're going to be looking at for most systems of interest in process engineering. And all right. So I think we're about out of time, which means we're probably going to have to finish this and work our examples on Wednesday. Is there any questions on condensation heat transfer or some of the expressions that we've kind of gone over? I know with a lot of it, like once again, that alphabet soup kind of feeling, but hopefully we can work a couple examples to give you guys more confidence on using these expressions on Wednesday.
Dr. Lopez, is that equation you just wrote down for horizontal tubes, is that for a certain range of Reynolds numbers?
That's a good question. It's typically for all Reynolds numbers. Primarily because unlike a vertical plate, the flow doesn't really get a chance to form a true flow regime. Because if we're looking at a plate or a tube, right, we have a system like this. This is the inside of the tube. And then the condensation rate is going to be kind of like this. And so the flow is going to be extremely limited. So your simple answer is, for horizontal tube, you don't have to worry too much about Reynolds number. You use this expression. Any other last minute questions? All right, if not, thank you guys for your attention today. I hope you guys have a great rest of your day and a great week. I will pop over to office hours in about 10:15, so if you have any questions, I'll be over there. But if not, take care.
Thank you.
Thank you.
Thank you.